Welcome to a video for section 4.6 of Math 3, which is on theorems about roots of polynomials. So just as a reminder, the word roots refers to solutions to a polynomial equation that is set equal to 0. If you are using the word zeros, that's talking about a polynomial function, and it's the values of x that would make y equal to 0. So they're pretty much the same thing. One's more about equations, one's more about functions. Okay, so let's talk about roots and how to find them. If you have a polynomial and it's factorable, then it's easy to find the zeros by just factoring it and setting each linear factor equal to 0. That's an easy case. If you have a polynomial that is not factorable, but it is a second degree, then we have another method that we can use, and that is the quadratic formula. This only works if it is a second degree. Third degree, fourth degree, and higher degrees do not use the quadratic formula alone. When a polynomial is not factorable and is not a 2 to second degree, it is not so easy to find the zeros. One thing that we can do is we can use synthetic division to quickly to divide, and we can see if we can find zeros by looking for a remainder equal to 0. We did this previously, and if we can find a number that divides in 2, so remember synthetic division looks like this, and you have a number on the outside, and you might have the coefficients here, and you bring it down, multiply, add, multiply, add, and we can see that we're looking for the remainder to be 0. This one that I just made up is going to have a remainder of, looks like 34. If that was a 0, then you would know that 2 is a root of the polynomial. So we could just try numbers until we get that, but that's not very efficient. There's a lot of numbers, and we can't just randomly hope that we're going to pick one. So there's an easier way to kind of narrow it down, and that is to use something called the rational root theorem. The rational root theorem is a way of creating a list. It's a list of all possible rational roots of a polynomial can be created by dividing all of the factors of the constant term by all of the factors of the leading coefficient of the polynomial. Now, before we move on, let's just review what this word rational means. Rational numbers are things like 2, -1, those are integers, 5/3, fractions. Things that are not rational would be things like the square root of 2 or 5 plus 3i. This is irrational, so this method will not find those, and this is imaginary. Those will have to be found in a variety of ways, but any of the rational roots we can use by finding this list. Okay, so let's take a look at an example. List all the possible rational roots of 2x to the third minus x squared plus 2x plus 5 is equal to 0. Then find all the real roots. And we're going to find both rational and irrational. Irrational are still real. Okay, so the first thing you want to do is you want to find the constants of, or the constant term. Let's see, so we need the constant term is 5. And so we need to find all of the possible factors of the constant term. So let's make a list. The factors of the constant term, which is 5, is a very small list because 5 is prime. If it wasn't prime, you'd have a longer list. So the only two things that multiply to make 5 are 1 and 5. Now, we're going to actually include negatives here. We could have a -1 and a -5, so I'm going to put a plus or minus in front of both of these numbers. Okay, so now we're going to do the same thing. We need to list the factors of the leading coefficient. Our leading coefficient is 2, just the 2. So let's make a list. So the factors of the leading coefficient 2 is going to be very similar to the list for 5, since 2 is prime also. You're going to have plus or minus 1 and plus or minus 2. So now we're going to create a, we're going to divide these, because this is not our list. We're going to combine these lists. You want to take these are going to be your numerator, and these are going to be your denominator. And so let's just start by taking plus or minus 1 and plus or minus 5. And we don't have to repeat the plus or minus on the top and the bottom. That's kind of redundant. So I'm going to divide by 1. Again, we don't need both plus or minuses. So dividing by 1 doesn't change anything, so nothing really happened. But now I'm going to take them again, plus or minus 1 and plus or minus 5, and I'm going to divide it by the other factor of the leading coefficient, 2. Okay, and this is your list. So how many numbers are in this list? Well, for each plus or minus, that's 2. So 2, 4, 6, 8. So this list of 8 numbers is that's it. That's all the possible rational zeros. I'm not saying these are all zeros, but the ones that are rational, that are zeros or roots, are going to be in this list. So we've narrowed it down significantly. So now what we're going to do is we're going to test them. Now I'm not going to have a lot of room over here. You can do this on scratch paper. So I'm going to go over here, and I'm going to do synthetic division. So going back, looking at my coefficients are 2, -1, 2, and 5. And I'm just going to pick one of these 8 numbers. So I'm going to start with, how about, just keep it simple, how about 1? Now, I only care about the last thing. I only care if this is a 0, the remainder. If it's not a 0 and I can figure out real quickly it's not going to be 0, I could just stop and start over with another number. Don't need to finish each one. So let's just go. Bring it down, multiply. Add, multiply. Add, multiply. I'm going to get a remainder of 8. Next, let's try -1. Same setup, just now I'm trying -1. Bring it down, multiply. Bring it down, or add, multiply. And look at that. I found 1. Okay, so once you find that 0, we're going to use the rest of this to help us figure out the rest. So this -1 that we found comes from a linear factor of x plus 1. Right? -1 would make this thing 0. And then the rest of it, we're going to use this 2, -3, and 5. So that's 2x squared minus 3x plus 5. That is equal to that polynomial, the 2x cubed minus x squared plus 2x plus 5. That polynomial would factor into this. Synthetic division helps you factor things that you didn't have other factoring methods to solve. Okay, but we need to find all the roots. I mean, you could just keep testing them, but you don't need to. If you take what you have left, it's usually something that you can factor. It's a quadratic. Let's see if we can factor it. So why don't you try and factor that, and then hit pause when you think you've got it. Or pause it, hit play when you think you got it. So trying to do the star method of factoring this, I could see that this is not actually factorable. And you can't assume that you can try to see if it's factorable, but if cases like this, where it's not factorable, then we need another strategy to solve this. So what we're going to do is we are going to use the quadratic formula. So I went ahead and used the quadratic formula, and what I'm seeing is I'm not going to get a real number. these are not real solutions. The solutions are imaginary. In fact, if I were to write this, this would be 3 plus or minus I square root of 31 over 4. So I found the only real root, which happened to be -1. So real roots, that's it. And the other two roots are going to be imaginary. So that brings us to something that kind of happens a lot, and we get imaginary or irrational roots. Now we're always going to find imaginary roots or irrational roots. Irrationals are like the square roots that don't simplify when you use the quadratic formula like this. Now if you think about the way the quadratic formula works, you're always going to have this plus or minus, and that's always going to give you two answers, one for the plus and one for the minus. And so because of that, the nature of the irrational and imaginary roots are always going to be in pairs called conjugates. So this is called the conjugate root theorem. So conjugates are two things that are pretty much the same. They're binomials, but one has a plus and then one has a minus. Think like a difference of squares when you factor it. Okay, so for irrational roots, if we have a polynomial, p of x, with rational coefficients, and p of x is equal to 0, then it has an irrational root of a plus the square root of b. Then the conjugate, a minus the square root of b, is also a root. So you just change, if you see one that has a plus, then you have one that has a minus. The same thing works for imaginary roots. This time you have real coefficients, and if a plus bi is a root, then a minus bi is also a root. So both irrational roots and imaginary roots have to come in pairs. So let's take a look at an example. A polynomial has roots 4, -8, 1/5, 4 plus the square root of 3, and -2 minus 8i. What other roots does it have? So 4, -8, and 1/5 are going to stand alone. They don't come in pairs because they are rational. Rational ones just don't have to come in a pair like the other ones do. Okay, but this 4 plus the square root of 3, that is irrational. And so we must include its conjugate pair, which is 4 minus the square root of 3. We just change the sign in the middle. Okay, then the next one we have is -2 minus 8i. This is imaginary. Imaginary is also going to come in a conjugate pair, so we need its conjugate partner, which would be -2 plus 8i. Okay, that's it for the first video. There is a second video that goes with this.